Water is being pumped through 750 feet of 6-inch Schedule 40 pipe. The discharge at the end of the pipe is 50 feet above the suction end. The pump is 80% efficient and is driven by a 20 horsepower motor. We're told the frictional loss is 50 foot-pounds force per pound mass, and if that is true, what is the flow rate through the pipe? So the first thing I've got here is a relatively crude schematic of our system. It's just showing that we have an inlet section, an outlet, and there's a pump somewhere in between. It's constant diameter, inner diameter. It's 6-inch Schedule 40 pipe. And we're told that the elevation difference between the inlet and outlet is 50 feet. Notice that we aren't told anything about any kind of bends or anything. The frictional losses are given to us as 50 foot-pounds force per pound mass. So I've assembled our given information. Note that we need to check our pipe tables. 6 inches is not the actual inner diameter. So we looked that up. The actual inner diameter is 6.625 inches. Make sure you're careful about that. Our pump horsepower is 20 horsepower. Our head losses, notice our head loss is given. This is not the units that we're used to seeing for head. They were a little more explicit maybe than what we needed to be, but this is foot-pounds force per pound mass. For water, we're using a nominal density of 62.4 pounds per cubic foot, and then I'm setting our datum, our reference level at position 1, which is going to be 0 feet. So if we start to assemble our information, we are asked to solve for the flow rate. All right, we're asked to solve for the flow rate. How do we do that? Well, I like to start with the Bernoulli equation, and I'm going to bring over the full Bernoulli equation. I like working with this and then starting to step through my system and step through each of these terms and figure out how we can simplify things. So number one, realize this is steady state. We've got constant mass flow of water. Water's incompressible. We're assuming the density at 62.4 pounds per cubic foot is constant. Position 1 is going to be at 0 elevation, and it is open to the atmosphere. Position 2 at the outlet is at 50 feet of elevation, and it's also open to the atmosphere, or at least at the same pressure as position 1. The pipe is constant cross-sectional area. So what that means is the linear velocity of the water is also the same throughout the entire system. No information is given about pipe configuration details. Right? We don't know, we don't know what the material construction is, so the surface roughness, aren't told any details about that. Nothing about fittings or valves or anything else, constrictions, expansions. But we are told what the head loss is. The only thing is the head loss is in a little bit different units than what we're used to seeing and what we have written as we have our Bernoulli equation written. And then we're told that the pump is 80% efficient. So what we need to realize is that this 20 horsepower, this is the pump rating, what's stamped on the casing of the pump. But what is actually delivered to the fluid, if it is 80% efficient, is only going to be 16 horsepower, is actually delivered to the fluid. So what we want to do is calculate, we're asked to calculate the mass and or the flow rate. So they didn't specify mass or volumetric, we can do both. So what we can do then is we can apply this Bernoulli equation from point 1 to point 2. Point 1 to point 2. So P1 is equal to P2. What does that mean? That means these two pressure head terms are going to cancel each other out. We just talked about U1 is equal to U2. Linear velocity at 1 is equal to linear velocity at 2. So that means that these velocity head terms are going to cancel out. Z1 is equal to 0. Z2 is equal to 50 feet. All right, we're setting our baseline at position 1. Is there any head extracted? Head extracted turbines? Nope, there's nothing like that. Do we have a head loss term? Yes, we have a head loss term, so we are going to have to keep our head loss term. What about head added? Yes, we have a pump in our system. We know what the power of the pump is. It is given to us in horsepower. It is not in head units. So we're going to use this equation to solve for the flow rate. It's a little tricky here because if you think about this, where is flow rate in this Bernoulli equation? Flow rate in the Bernoulli equation a lot of times is in the velocity term. But what did we just do? We just canceled out our velocity terms. So where is that going to get us? Are we going to be able to solve for flow rate? Well, if you think back and look in your textbook and look at your notes, what you'll realize is that the power of a pump is related to the head added by the flow rate. And we'll go through those calculations. So your flow rate is going to be buried inside this head added term. So don't get into a panic for canceling out these velocity terms and feeling like you're losing all information about the flow rate. You should realize that your head added term, your pump power term, is going to include the flow rate. So let's now start working with this equation, simplifying it. And the other thing we need to do is realize that we need to deal with some dimensional analysis. And so this head loss term is given to us as 50 foot-pounds force per pound's mass. And so what this is an energy per unit mass basis, per mass basis. This equation here is written on a per weight basis. And so what we're going to have to do is we're going to have to take this per mass basis and convert it to a weight, a per weight basis. And we do this, and this might be a little kind of not quite totally intuitive at the beginning when you're working these problems, but we do this by dividing by g so that we have m times g in the denominator, but then we have to multiply by gc. And so that will give us our head loss term in per weight basis. So here's our G sub C. Remember, G sub C converts pounds force to pounds mass, and in MathCAD, pounds force is explicit LBF. Pounds mass is just LB. So this is our GC. Our head loss term is given to us in foot-pounds force per pound mass. And so we divide by G, basically mass times acceleration due to gravity. That's the weight. And then we need to multiply by GC. Now, because the numerical value of GC is the same as G, we're assuming we're at sea level, that the force of gravity, or the acceleration due to gravity, is 32.174 feet per second squared. MathCAD has G built in, so if I just type G and I want that in 32.174 feet per second squared, notice our numerical value is the same, 50 feet. Our numerical value for head loss is the same at 50 feet. So it's tempting to just take the shortcut way and just say, oh, head loss, let's just, pounds force cancels pounds mass and we're left with feet. That's not how it really works. And I think to make sure that you don't make mistakes in the future with even more complicated problems, I think it's very valuable, and MathCAD makes it easy to work through these units to make sure that you're dimensionally consistent at each step of the process. So now we've got our head loss term in units of head, and so we can go through. I've got these simplifying assumptions written down. We can cross out terms in our Bernoulli equation, and our Bernoulli equation becomes head added minus head loss, that's the only terms left on the left hand side, is equal to Z2. And Z2 we know is 50. So again, going back, we were asked to solve for flow rate. Where is flow rate? Flow rate is not explicitly listed here. Well, as we mentioned, flow rate is buried inside the head added term. And so if you go back to your notes, you can see how head is related to power. So head added is energy per weight of fluid. Energy added per volume is head added times the weight of the fluid, and then power is the energy added per volume to the volumetric flow rate. So go through your notes in that section, make sure you are familiar with these concepts. We can solve for the head added. Let's just go ahead and solve for head added and get that out of the way. So that's Z2 plus head loss, that's 50 plus 50 is 100 feet. Head added is 100 feet. This is the amount of energy that's actually applied to our fluid that is flowing through the system. Now, we need to convert this, we need to relate this to the power of the pump. So the power of the pump was given to us as 20 horsepower. But remember, we were also told that that pump is only 80% efficient. Of that 20 horsepower, only 80% of that is actually being applied to the liquid, which is what this head added term represents. And so the power actually going to the water in our system is 20 times 80%, which is 16 horsepower. And so now what we can do is we can take this power that is actually going to the fluid and relate it to the head added. And so if you look at your notes, there's several steps that you can take. Power is equal to head added times rho g u a. Well, in this case, we know what, let's see, we know what, are we given the water is pumped through? I'm trying to remember. Are we given the flow rate? Or sorry, we're solving for the flow rate. My mistake. We're solving for the flow rate and the volumetric flow rate, that is. And so we can use this part of the equation. So we can solve this for Q. And so if we do that, sorry about that little mess up there. If we do that, we get this is the power actually added to the fluid divided by head added times rho g. That is equal to 1.41 cubic feet per second, or about 633 gallons per minute. And if we wanted it in terms of mass flow rate, we simply multiply our volumetric flow rate times the mass flow rate. Think about our answer. Does the answer seem realistic? Yeah, I think it does. You know, it's kind of hard to visualize some of these flow rates because we're not used to really thinking in terms of volumetric flow rate that much. Notice that we did not need anything, like I said, about the pipe configuration, valves, or anything like that. The head losses were given to us on a mass basis, and because I like working on doing my Bernoulli equation calculations on a weight basis, I think it's easier to do that. So remember, work through this, make sure you're comfortable with doing these kinds of problems in both SI units and imperial system units to be able to convert these, and make sure you know what you're doing and aren't just blindly just kind of fudging through and canceling things out that shouldn't really be canceled. So that's this problem, a nice little exercise in figuring out the relationship between head and power of a pump.